meeting.
So we have 1 hour lunch.
No, we have got so much to do that we're going to take a 45-minute lunch. I'm going to miss most of the meeting, but I wish I could take a 2-hour lunch and go to the whole thing. So, all right, this is just for your information, but the thermal expansion of water is very strange. So if you look at this big picture, it seems reasonable that you've got this nice linear drop in the volume of water as temperature changes. But if you examine this curve at the range from like 0 to 5 degrees Celsius, it's not exactly linear. You actually have this dip in the graph. This dip allows life to exist on Earth. This is what makes water so cool and unique. This says that instead of the volume of water decreasing and thus the density increasing with temperature dropping, there's a very small period of temperature range, I should say, right close to where temperature freezes, where as the temperature drops, the volume actually increases a little bit and the density decreases. And what this means is when a lake starts freezing, the top is going to be the coldest because that's exposed to the air, and you get warm water on the bottom, and the warmer water is less dense because of this little property. So the warmer water is what sinks, and the colder water is more dense, so it rises. But it's only because of this little curve that happens. So you get a frozen top of the lake, but everything else in the lake survives all winter long. So the algae, the fish, whatever eggs are clinging onto things. So this allows things to survive the winter. But if we had mercury lakes, which would be weird, we wouldn't be able to survive. Well, we might be a different species, who knows? But you'd have the frozen part would be the bottom of the lake with the liquid on top, and so that would make life it would be very challenging for life to exist for a whole year if that was how life was. So that's why when they're looking for planets that could potentially host life, sometimes they look for planets that have liquid water. Since we know that that's a pretty key element to life on Earth, they suppose that that's probably a pretty key element to life on other planets as well. So. Okay, thermal energy. We have to have a little conversation about what system versus environment means. So, because the wording sounds weird to me. I don't know. Maybe it doesn't to everybody else. But system is just the object or objects, and the environment is what surrounds them. And it's confusing to me because system, for me, feels like a synonym for environment, but it's not that case in physics. So system is the object or objects, and the environment is what surrounds it. And so we'll denote the temperature of the system as T sub S. The temperature of the environment is T sub E. And as we learned with the zeroth law of thermodynamics, if those temperatures are not equal, then they're going to come into thermal equilibrium. So your system, if it's hotter than the environment, will give up heat energy to the environment and warm the environment up, and the object itself will start to cool down. If the other case is reversed, the environment is hot and the object is cold, the environment will transfer energy into the cup, the object, if it's a cup, why am I thinking cup, and warm it up. So that's thermal energy being transferred. And this is, in terms of kinetic and potential energies, the thermal energy is just associated with the vibration of the molecules. So the more hot an object is, the more the molecules are vibrating. Okay, heat, in terms of physics, might not be exactly what you learned heat was in everyday language. So heat is a form of energy. We use symbol Q for heat. And this is what gets transferred. When we talk about the system and environment transferring energy, they're transferring heat to each other. So when something is getting heat, it doesn't necessarily mean it's getting hotter, because heat doesn't necessarily have to be an increase in heat. You can have a decrease in heat as well. So if energy is gained from the environment, then you have plus Q. If energy is lost from the system to the environment, then you have minus Q. And if Q equals 0, then the energy, the system and the environment are in equilibrium. There's no energy transfer. Yeah?
Is this the same as enthalpy in chemistry?
No.
No? Okay.
It's marginally related, but not the same thing. So heat is not an intrinsic property of a material, but before scientists understood that, they thought that heat was measured in terms of its ability to raise the temperature of water by 1 degree, and that's how we get the definition of a calorie. So to figure out the calories of food, they literally burn the calorie, or burn that food. They burn it to dust, and they figure out how much temperature it gained during that process. So 1 calorie is defined as the heat required to raise 1 gram of water by 1 degree Celsius. 1 capital calorie, so when you eat food, it's measured in capital calories. That's 1,000 lowercase calories. And the British thermal unit is based on the calorie. So BTUs are part of the British imperial system of units. So BTU is a measure of energy, and it's defined as the heat required to raise a pound of water by 1 degree Fahrenheit, which is weird. And so there's the conversion from calories to BTUs to joules down at the bottom. And so how the calorie was defined doesn't make a whole lot of sense anymore, since we know that energy is transferable. It's not intrinsic to an object. It can give up its energy. It can take in more energy. So the calorie is not an SI unit. Joules are the SI units. If you take a RE class in energy, a lot of things you measure will be in BTUs, so you'll get used to this conversion. But in physics, we don't use BTUs very often. All right, quantity of heat. We can change the temperature of a body by doing work on it, or by adding heat to it. So you can put a flame under water and make it heat up, or this is a way you can do work on the water. You've got a little spinner in this cup, and by moving this pulley, this mass up and down, that turns the crank that spins this. That spinning motion adds energy to the water, and it heats the water up. So if you're, you can transfer heat into or out of a system being the water, and then measure the temperature change. So the heat transferred is defined as MC delta T. And I'm always trying to find silly ways to remember equations, so I remember this one because it looks like MCAT.
So then the M is mass?
The M is mass. C is a new variable called the specific heat. That's going to be dependent on the material, so you can look specific heat up in a table. And then delta T is change in temperature in the appropriate units. So if you look up specific heat and the units for that value is in Kelvin, then you've got to convert your temperature to Kelvin. Generally, it's safe to just assume every temperature needs to be in Kelvin. There are some instances when you can keep things in Celsius, but if it gets overly complicated for you to remember, then just convert everything to Kelvin to be on the safe side. And I didn't write down what table the specific heat is. Anybody have their, probably nobody has their book open.
What are the units?
Heat is energy, so joules.
So even if we do everything in Kelvin or everything in Celsius, it'll still be the same number at the end, which will be joules?
Yes, so if you do, well, it depends on what C is, because you can find, let's see, let me find the table and I'll see what values you get, because sometimes they'll do things in terms of joules per kilogram times degrees Celsius, and that would still give you joules, because you've got the delta T. So if you're taking a delta T in your equation, the step size when you take a delta T would be the same as whether you're in Celsius or you're in Kelvin. And so if you are taking a delta T, you can stay in Celsius, but it does depend on what units you use for specific heat. Let's see, we're in chapter 17. All right, so in table 17.3 only gives specific heats in joules per kilogram times Kelvin. So again, if you're solving for Q, then you've got a delta T in there, so you can keep things in terms of Celsius, since the delta T would be the same whether it's in Celsius or Kelvin. But if you were solving for one of the temperatures and you were given the Q, then you're going to have to convert the other temperature to Kelvin in order for your answer to be correct.
That would be safe since it defaults to Kelvin all the time.
Yes, yes. If it's just too confusing to figure out, then just convert everything to Kelvin. Chris, did you have a question? Okay. Not anymore. Here's some conversions if you feel the need to write them down. The one from calories to joules is pretty handy, so I'll write this. So 1 calorie per gram times Celsius degrees equals 4,190 joules per kilogram times Kelvin. That's a conversion I feel like comes up often enough that I want to write it on the board.
Often enough to be on the test.
Well, you don't have to memorize any conversions. All the conversions are on your sheet of notes, so. Okay, 1717. Or 17.7, excuse me. All right, so we're going to get some practice using this heat equation, and I'm going to do this one for you because there's a really good way to set these problems up that I think makes them go quickly, and it's all about being organized. This is the name of the game today with these calorimetry problems, is staying organized. So we have a camper that pours 0.3 kilograms of coffee initially in a pot at 70 degrees Celsius into a 0.12 kilogram aluminum cup initially at 20 degrees Celsius. What is the equilibrium temperature? Assume that coffee has the same specific heat as water and that no heat is exchanged with the environment. So the heat, there's heat transfer going on. Who's giving up heat? Who's gaining heat in this problem?
Cup is gaining heat.
The cup is gaining heat. Okay, so that's our bit of logic here. That's your first question, is who's giving up heat, who's gaining heat? And in this case, we only have 2 objects. Sometimes you'll have more than 2 objects, so you need to put them all into this logical relationship. So Chris said that the coffee gives up heat. So it's got a minus Q. And that is equal to the amount of heat gained by the cup. Okay, so this is really important that we get the signs right on this, or else our answer doesn't work out right. Another way you can do this is just set everything equal to 0. We can see that if you just do Q coffee plus Q cup, then the sum of the two should equal 0. So whatever works logically for you is great. So the organized part, I kind of skipped ahead, but that's what we want to do before we set up our logic is make ourselves really organized here. We've got coffee, and we've got a cup. They both have mass, so M coffee and M aluminum. So the mass of the coffee is 0.3 kilograms. The mass of the cup is 0.12 kilograms. The specific heat of coffee, we're using the specific heat of water for that. And the specific heat of water is 4190 joules per kilogram times Kelvin. The specific heat of aluminum is 910. Okay, now the coffee has an initial temperature. The cup has an initial temperature. So the coffee's initial temperature is what? 70 degrees Celsius. The initial temperature of the cup is 20 degrees Celsius. And what we're looking for is the final temperature, which is the same for both of them. So since we're solving for one of the temperatures instead of something else in the equation, this is an instance where you've got to convert everything to Kelvin. So how do we convert 70 degrees Celsius to Kelvin? Okay, what does that equal?
343.15.
Okay, now if we add 273.15 to 20, what do we get? 290.15? 293? Okay. So we've done the logical part. The rest is just putting the equations together. Okay, so I like this equation, so that's the way I'm going to write it. So I have a minus the mass of the coffee, the specific heat of water, which is the specific heat of coffee, times the change in temperature for coffee equals plus the mass of aluminum, specific heat of aluminum, the change in temperature of aluminum. Then we can bust out what's inside the delta. So we have T final, which is the same for both of them, minus T initial coffee. And then on the right-hand side, when we bust out what's in the delta, we have T final minus T initial aluminum. So the variable that we're trying to get together algebraically is T final. That's what we're trying to solve for. We have every other value, so at this point it's just algebra. So this is the physics done. The rest is algebra. Do you guys want to take the time to work on the algebra? Right now?
Yes.
Okay. Spend 5 minutes trying to work through the algebra and see if you can come up with the correct answer.
I don't understand the equation up there where you have negative Q equals positive Q.
So that's all based on the thermal energy transfer. So something has heat and it's giving up heat to something else.
Yeah.
So the coffee has the heat and it's giving its heat to the cup. So the coffee is going to lose that same amount of heat. That's why it's got a negative sign, because it loses that heat, and then the cup is gaining the heat, so it gets a positive sign. And those have to be equal, since the heat can't be lost to the environment. So we're assuming however much heat is lost from the coffee is exactly the same amount of heat gained by the cup.
Oh, okay. I was thinking like the negative, as in it'll be a negative number, and how can that equal a positive number?
It's just when you move that negative into the equation, it all works out, because if your T final is going to be lower than your T initial, so the delta T for the coffee would end up being a negative value, and the negative out front gets rid of that. So if you don't have the negative out front, then you end up with a negative temperature, which doesn't make sense.
Well, since we're using it that way, then how, coffee cup, how is this number equal to a positive number if this side is negative? Because negative isn't equal to a positive, if for this equation to be true.
Well, you'll get the Q will be a negative value. So you have to have a negative out front for it to equal a positive value. So the Q for the coffee will be like negative 500 joules, right?
So it's parentheses, and then...
And that value will be like negative 500, so you have to have a negative out front
Negative
to give you a positive for the cup.
2, like that?
Yeah,
Okay.
yeah.
So, is that always going to be the case where there will always be a negative out here in front?
For whatever's losing heat,
Okay.
yeah.
And since that is true, then Q, in the end, these will both be positive.
Yeah,
no matter what.
once you factor in this negative, then you'll have like 500 equals 500, and you won't have a mismatch in signs when you're done.
All right.
Yeah.
And what's your logic for combining these equations? I don't understand that.
Why do I set Q coffee equal to Q cup?
Well, now the MC and like the whole algebra thing you're doing there. The
So
large.
what we're looking for is T final, and they're coming to thermal equilibrium. So the T final for the coffee is equal to the T final for the cup. So when I write out the equations, I know that that T final on the left side of the equation for the coffee is equal to the T final on the right-hand side of the equation for the cup. And so all we have to do algebraically is try and get those together and solve for that one T final value.
Okay.
Yeah.
Finish the classwork. Super C, does that mean magnetic field energy is decreasing with time? Well, if it's positive, then it's not decreasing.
Thermal energy is developed in the inductor. But the power was based on the resistance. Magnetic field energy. I don't have a freaking clue.
Okay.
I'm going to look in the book. It says, no, if I is constant, then the stored energy U is constant. The energy is being consumed by the resistance of the inductor. The energy being consumed by the resistance of the inductor comes from the EMF source that maintains the current. It does not come from the energy stored in the inductor.
I'm just going to put no.
Okay. I don't know that. Yeah. You can tell that I don't grade that problem. I'm pretty familiar with the answers to the ones I grade. Oh, is it noon? All right. Any questions on this problem before we break for lunch? Oh, is this thing still recording or? Shh, okay, I'll have to clip.